Hi, I am Rasmus Benestad, and I am a senior scientist at the Norwegian Meteorological Institute. And I will give an introduction to climate research and climate services at the Norwegian Meteorological Institute. So when I do that, before I do that, I'll share a screen with you, a presentation. So this presentation was given at the SNOWAMP 2 final seminar in Oslo, 13th of December 2022. And the reason why we carry out climate research and have climate services is because of global warming or climate change that will affect society and nature, and to which we need to adapt. So in that respect, some of the questions that we are interested in is, what are the consequences for us from this climate change? And how shall we adapt to a new climate reality? But also, how can we get the best possible information and knowledge about future outlooks? So some of the aspects that we are involved with in climate research involve global and regional climate models. So the global climate models are a primary tool for looking into the future. They can simulate how the climate changes in the past and the future, given some assumptions about how the greenhouse gas emissions are changing as well. One thing with the global climate models is that they are very crude because they need to calculate what is happening over a long period, say hundreds of years, and they also have to take into account slow changes in the oceans and also the surface. So they need to include both the atmosphere, oceans and surface, and also the cryosphere or ice processes. And then they have to do a lot of calculations for various components of the Earth. Although the atmospheric aspects of the climate models are very similar to the weather forecast models on a global scale as well, whereas the global weather forecasts only are carried out for the next few days or maybe couple of weeks, and they don't have to take into account the slow changes in the oceans because they're so slow, so they don't really matter. So the weather forecast models have a much higher spatial resolution. So these models, they represent the Earth by a grid mesh, and each mesh is a grid box. And weather forecast model has like an advanced one would have grid boxes of the size of 8 kilometers, so they're very high resolution, whereas a global climate model has a more typical 100-kilometer resolution. So the global climate models do not really represent the topography and the mountain ranges very well. So, but we can use what we call regional climate models instead, which focus on a smaller region and maybe don't even take into account the oceans. So they have a much higher spatial resolution, and they get a better representation of the mountains and topography. So the regional climate models also simulate the dependency between the large-scale conditions and the small-scale climate. And this is what we call downscaling. The regional climate models are only one approach for doing that, because we can also use statistical methods, which I will explain later on. But in a sense, downscaling involves adding in information to the equation. So the global climate models tell us about what will happen on a large scale, and then we also need to add information about how the local climate depends on the large scale climate, and also how it depends on geographical conditions as well, specific for certain sites. And then we can use them to estimate how the temperature or rainfall typically will change, or how their statistics will change. And then we will look at the mean values and also extremes. Both are important in different respects. And in this case, I will also distinguish between data and information. So data is the output of the models, or they are the numbers we get when we measure the temperature or rainfall, whereas information is more like, say, summary statistics or like patterns in the numbers that represent processes that you see the fingerprint of in the data. And the climate services are used to provide both data and information to the public and decision makers. And I would argue that most decision makers will make a decision based on information rather than data. But data are useful for the users who want to carry on further data analysis to extract further information from the data. So I will give an overview of the Meteorological Institute of Norway's approach to downscaling based on a quarter of a century's experience. And if you see this picture, it shows a rain gauge, and it's a small bucket with a diameter of a few centimeters, in which we collect the water that falls down from the sky, like rainfall or snow. But the global climate models have a coarse resolution of 100 kilometers. So how can we make these inform us about how much water these rain gauges are going to collect in the future, maybe in the next 100 years? And luckily, we're not trying to estimate how much rain it will collect on a certain day, but we are looking into how the rainfall statistics is changing. So like we look at how the amount over a whole year, and typically how much the amount will change from year to year, for instance, or the temperature, how the temperature statistics will change rather than on an individual day, a particular day. So when we talk about statistics, I tend to use the term statistics to describe probabilities, which are shown here. So the x-axis here represents the temperature on the left and rainfall on the right. So this is the amount of rain each day, and this is the temperature. And these curves, the gray curves and the red curve, show two examples. So the height describes how common these are. So you see that the highest peak here is in the middle of this curve on the left there. It's a normal distribution, so it can be described by the mean and the standard deviation. And the most common temperature here is slightly higher than 15 degrees for the gray curve, but for the red curve, it's 20 degrees. So these curves could represent the temperature statistics at different sites. Or they could also represent the temperature at different times, for instance, in the past and the future. So then the changing the shape of the curve basically is what we call climate change on a local scale. And the same thing for rainfall. When it comes to rainfall, we don't have negative rainfall. So we have, but we have a lot of days when it doesn't rain. So what we do is to divide the days into rainy days and non-rainy days. And then the fraction is basically the wet day frequency that tells us how often it rains. And then we can look at the amount we get on the rainy days, and we can organize them like this, so that we stack the number of days up according to how much we typically receive on a day. And we see that most of the days we see a less rainfall amount, and then there are fewer days when we see more than, say, 30 millimeters. The nice thing with this curve here is that, or the rainfall, is that the daily rainfall, when we look at rainy days, is almost exponentially distributed, which are these curves there. And that can be described by one parameter, the mean value of the rainy days. So we have two very simple curves with only a few parameters that can characterize the statistics. So for temperature, it's a mean and standard deviation. And for rainfall, it's a mean and a wet day frequency. The nice thing is then that the statistical properties are fairly robust and predictable. So if we can say that climate is weather statistics, then we see that the climate is more predictable than weather. We can see that here from these two illustrations here. One shows the mean temperature and the other one shows the mean rainfall. And we see that the mean temperature is lower at the high latitudes around the poles and also at the high elevations, but the mean temperature is higher around the equator. But also you can see the effect of the oceans as well. And similar with the rainfall is that there's a band of higher, more intensive rain around the equator, and also you can see that there's higher amounts, like in the regions where we see the storm tracks over the oceans, and less over the subtropics. And also the weather statistics or probabilities are also useful information for decision making. So if we look at the rainfall statistics in particular, then we see that the global states also affects the local statistics. So when the global hydrological cycle goes faster around, that will also affect the local rainfall as well. And then we see that it's also influenced by geographical conditions as well, as you see here, like mountains and also the oceans. So it's fairly predictable. So we want to downscale statistical properties, and that is a bit equivalent to adding further information to like the global climate models, which tell us how the global climate changes. And then this information is about how the local rainfall statistics or the local temperature statistics depends on like a large scale conditions in the area around, or teleconnections, or local geographical conditions. It's also worth mentioning that the global climate models have a minimum skillful scale, and it's due to the way they are designed. So like the way they solve the mathematics is like they use, they don't have continuous number scale, but they have discrete number scale, and they use like specific algorithms, but also approximations to solve the equations that represent the physics. So they don't really give a very accurate description like on each grid point, but like if you look at 8 by 8 grid points, you will see a pattern that looks very similar to what you see in the real world. We also like to, when it comes to climate change adaptation, like downscaling, it represents one of 3 different approaches or strategies for making use of the climate information that can help us making better decisions. So downscaling gives us the best description of the regional climate outlooks, and then also stress testing or synthetic storms can help us improve our preparedness, and I'll come back to that later. And sensitivity tests tells us what aspect of climate change is most important. Is it the rainfall, or is it the temperature, for instance? So when it comes to downscaling, we have 2 different approaches at the Norwegian Meteorological Institute, and it's the dynamical downscaling that involves regional climate models and empirical statistical downscaling. And I would say that you should not use either dynamical downscaling or empirical downscaling, but you should use both. And the reason for that is that they make use of different assumptions, which are very independent of each other, very different. So if you get the same results, which you should do, then you have a bit more trust in the results than if you get different results. And then you have something to explain. You have to understand, why do we get different results? Is there something that went wrong? Also, they have different strengths and weaknesses, so they complement each other as well. So it's very handy to use both of them together. So, but I would really strongly urge that you should always use the dynamical as well as empirical statistical downscaling, and not only once. Here's one example of statistical downscale results, and these are gridded scenarios. So we downscale like a group of stations, and then we can then grid them the way we would grid observations to get like a map here. So and we could do that for both temperature and rainfall. And typically, we would downscale, like say, seasonal mean range temperature as shown here, or seasonal mean precipitation. This shows the December, January, and February DAS is temperature near the surface, or air temperature near the surface. We see that statistical properties are easier to downscale than like each individual days. We also will downscale large model ensembles, and I'll come back to that later. But one reason is shown here, and it shows like the 95 percentile of the ensemble. So we have here we have 151 different runs which have been downscaled, and because the global climate models reproduce the random or stochastic variability, or like change, year-to-year variations, which is due to the chaotic system. Then when we have 151 of them, and they tend to cover like the whole range, like interannual range, that we see also in observations. And then if we take the 95 percentile of that, we will capture like a typical warm winter, or like a potentially possible warm winter in the future. So this is like 1 in 20 warm winters that is possible, depending due to the natural variability or due to year-to-year variations that are hard to capture with just one or a few model runs. In this case, because we're looking at the large multi-model ensembles, we also have to archive the data in a different way, because the conventional way is very slow and also takes up a lot of space. So in this case, we have around 1,000 downscale runs, and they are gridded on an 8 by 8 kilometer grid. And we can represent that with 475 megabytes for like 100 years almost, making use of something we call empirical orthogonal functions that will actually keep the salient information stored in this data, but throw away a lot of noise. And also that's a fast way of dissecting the data and visualizing the data as well. So it's a fast way of dealing with the data. And we downscale statistics, as I said, and for instance, we would estimate probabilities of like a heat wave occurrence, and also duration of wet and dry, or cold and hot spells. And this, I'm going to get a pointer here. So here you see like a figure here on the right, which compares the number of days over like a hot spell against like what you would expect from a geometric distribution. So we use a PDF to represent the duration of heat waves, and we try to downscale these statistical properties. And the lower panel here shows a probability of at least 5 days of 35 degrees, and that is based on both the occurrence, but also that the event will last more than 5 days, like more than 5 consecutive days. We can also look at the probability of receiving more than, say, 50 millimeters a day, or like 20 millimeters a day with rainfall, or the shape of intensity, duration, and frequency curves. And here you can see one example. You see that the shape of these curves are fairly simple, so they can be represented with like a simple formula with some parameters, and we try to downscale these parameters that describe how these shape or what they look like. So the upper curve here represents a 100-year return period, so that these are rainfall at certain time scales from like few hours to 24 hours. And so it's the intensity of rainfall, and you see that the most intense rainfalls occur very rarely, like say once 100 years, whereas you also have the lower curve here, it's like every 2 years. So these occur more frequently. We also combine the regional climate models and empirical statistical downscaling in what we call hybrid downscaling. So we use the output from regional climate models to calibrate our statistical methods. And this is also called to the reality. The advantage of that is that with climate model results, we don't have any missing data or any data gaps. And also it's easier to find a connection between a large scale and small scale as well. And this enables us to overcome the so-called the law of small numbers, because if you have like a small number of ensembles, like of runs or simulations, and they all are represent both like the climate trend, but also natural variations on top of that. And these variations are very pronounced on a regional scale, even though when you look at a global scale, you don't really see them at all. Then they can give misleading numbers for like a given region. And that was demonstrated by a study by Des et al. In 2012, where they ran the same model 40 times. And it started off with the same conditions, apart from one thing, and that was in the atmosphere, which started off with different days in the atmosphere. And as they let it simulate the time onwards over like the years, these differences would grow and become very big. And they would give very different evolution of temperature and rainfall for the next 50 years over regions like North America, and also like on a smaller scale as well. But also once we have carried out this hybrid downscaling and calibrated models, then we can apply them to a large number of global climate models. So we can combine this with large multi-model ensembles, and then we overcome the law of small numbers. And in addition to downscaling, we have this stress testing or synthetic storms. And in this case, it's a non-scientific approach. It's more like a engineer approach. So it's very practical. And we look at past weather forecasts because we know of past extreme events, and we then ask the question, what if this event hit us? And it's useful if you have impact models that you want to study how that would affect the flooding situation or the wind stress, or if your community would be able to cope with that. It's also useful for preparedness exercises and study the response to that. So here's one example from Kulna. So we took the forecast from Hurricane Matthew, so in this case the rainfall and also the wind field, and then we moved them over to Kulna and then said, okay, what would happen if a typhoon similar to Hurricane Matthew hit Kulna? And the nice thing here is that it came from the south to hit Haiti, and also would come from the south to hit Kulna, and over the sea, the surfaces were very similar whether you are near Haiti or near Bangladesh. And then we have sensitivity testing, and then if we have models for or impact models for describing runoff or agriculture or economy that are quick and cheap to run, we can run them many times, and we can run them with the observed temperature, but then we can change the temperature or like add a degree or reduce a degree or add, we can remove some of the rainy days, just replace the amount with 0, or we can add rainy days, so we can scale it up, so we can multiply by 1.5, for instance, or 2 to simulate like more intense rainfall. And then we keep track of the input and the output in, like, say, the statistics of input and output to see which aspect or what will give the largest response in the model. Here's one example. This is a crop model. So this it predicted the yields of maize, and then with different temperatures. So then we have temperature change. We see that for low temperatures and also very warm temperatures, we get a reduced gain, whereas there's like an optimal temperature, which is a bit, well, 1 to 2 degrees higher than present. So I'm coming in for landing now. So when we want to get regional climate information for decision making and climate change adaptation, we really need to combine dynamical downscaling with empirical downscaling. We should not use either or. And this example shows why. So the blue curve here and the blue field shows dynamical downscale results based on 4 global climate models. And then the red one shows empirical statistical downscaling for the same global climate models as the dynamic downscaling. And you see that they give fairly similar results, so they follow each other. So we have confidence that they actually provide us with numbers that we can rely on. But we also carried out empirical statistical downscaling on a much larger ensemble, so with many more simulations of global climate models, and we see that the ones we picked only represented a small range of the possible outcome. And this is like what I mean by the law of small numbers, is that when you pick a small sample, then you don't get a robust result, and it can vary from if you pick, say, one set or another set, you can get very different results just because you pick different by random. So you need to pick enough model runs in order to actually get a robust statistical sample that will not change very much if you add a few more models or reduce a few more models as well. So we apply the downscaling to many climate model simulations. We downscale statistical properties because they are more robust and more predictable than individual days. And in addition to downscaling, we would recommend stress testing and sensitivity testing to get a better understanding of how the changed climate will affect the society, but also what is the most important in terms of, say, like the runoff or agriculture. Because we are looking at ensembles rather than single runs, we also need new levels of evaluation. So we need to see whether this ensemble describes the statistics well of what we observe as well. And evaluation is really important, and I haven't actually talked much about it, but all climate model simulations need to be evaluated, or all methods need to be evaluated and tested and checked that they actually do what we think they do. So this is a unique Norwegian strategy. I don't know of many other groups where that uses both statistical and dynamical downscaling and also large ensembles for making regional or local climate projections. So the work that has been done here in our group includes 7 of us, and we carry out the analysis in R, and that's we have built an open source package called ESB for easy climate analysis. And it's available on GitHub, open source. So basically, we have some information, and we add more information, and then we get even more information. That's the essence of this. We collaborate internationally, both with the Nordic countries, but also Arctic countries, like through AMAP, that's the Arctic Monitoring and Assessment Program, but also through Europe. And we have some projects in Mozambique where we collaborate with the National Meteorological Services there, and also Southeast Africa and in Bangladesh. We've had some collaborations with India and also with the World Meteorological Organization. Thank you very much.